Because enthalpy is a state function, this leads to a particular concept called Hess's law. So let's imagine that I take water as a solid and I change it, I melt it into water liquid. That process requires a certain amount of energy, delta H, and this would be the delta H of melting. Now, if I take that same liquid water, and I change it into water vapor or water as a gas, this will also take some energy, and that will be the delta H of vaporization. I've done a process in 2 steps. So I've taken water and turned it into liquid, and then taken that liquid and turned it into gas. The net result of that is that I have taken my solid water and I have turned it into a gas. That requires an amount of energy equal to the sublimation enthalpy for water. So notice that I can either simply take the solid water and turn it into gas directly, sublimate it, or I can do 2 steps, take the solid water, turn it into liquid, take that liquid and turn it into gas. So this liquid state is an intermediate state, and when we calculate or figure out the delta H for this process, we will find that if I add up the delta H for the melting and the delta H for the vaporization, it will equal the delta H of sublimation, because the overall process has to have the same change in enthalpy as the 2-step process. So adding up the 2 steps has to equal the amount of energy for the overall process. So this works with any chemical or physical change. If you do it in multiple steps, the net result is always the sum of the amount of energy needed for the 2 steps. Let's do an example to see how this might work. So in this problem, I'm trying to calculate the change in enthalpy for this overall reaction given these 3 steps. So I need to be able to put these 3 steps together in such a way that it gives me this overall reaction. So the way I'm going to approach this is, first of all, to figure out where my products are in the 3 steps, and this C2H2 compound only shows up here in this particular reaction, the first step. And then my carbon solid shows up here, and that's the only place that shows up, and my hydrogen gas shows up here, and that's the only place that it shows up. So I can see that I'm going to want 2 of these carbon solids. So I only have 1 in this step. So if I multiply this step by 2, that's going to give me 2 of these. I need 1 of these to start with. So I have 1 here. So this step is going to give me 1 of those. And I need this, but I need it to be in the products and not in the reactants. So I need to write this reaction backwards. So let's see what that would mean in terms of the enthalpy. So if I start with my initial state being C2H2 plus oxygen, and then I end up with a final state that has 2 CO2s plus a water, then this is the direction I'm going as the reaction is written in this way, from these being the initial state to this being the final state, my products, final state, my reactants, initial state. And that amount of energy is minus, so I'm going downhill in energy, that amount of energy is minus 1299.5. So if I go the other way, if I start here and go up here, what you can see is that the change is exactly the same, but now I'm going uphill in energy, so the sign has changed. So if I flip this reaction around, then the sign of my delta H will change. So if I write 2 CO2 plus water goes to C2H2 plus 5/2 O2, that delta H, standard state, is going to be positive 1299.5 kilojoules. Now, what happens if I double the amount of reaction that I do? So if I remember that this is kilojoules for this particular reaction. If I do this reaction twice, I get this amount of kilojoules for the first one and this amount of kilojoules for the second one. So if I do this twice, I'm going to multiply my energy by 2. So I'm going to get twice as much energy if I do the reaction twice. So if I write 2 carbon solid plus 2 oxygen gas gives me 2 CO2, then that delta H is going to be equal to 2 times minus 393.5 kilojoules. And then finally, if I do that last step, hydrogen gas plus 1/2 an oxygen gas goes to water as a liquid, I get exactly the amount of energy that is reported in the problem, because I've just done that reaction exactly as reported. So now let's see what happens if I add all of these reactions together and see if I get the overall reaction that I'm interested in. So I have 2 CO2s here and 2 CO2s here. So I have it in the reactants and then I have it in the products. So it's made and then it's used up, so it goes away. So I can subtract out those two things. And then I have water as a liquid here, and I have water as a liquid here. So it's made and then it's used up. So again, those guys are going to subtract out. And then I can see that I have 2 oxygens plus another 1/2 an oxygen. That's the same as 5/2 oxygens in the reactants, and I have 5/2 oxygen in the products. And so those are going to subtract out. And then that's all I have left. And so what I have left that hasn't been crossed out is 2 carbon solid plus hydrogen gas goes to C2H2, and that's a gas. And that is exactly the reaction that I was interested in. So when I add these reactions, I get the reaction I want. And when I add these reactions, the total delta H is the sum of the delta H's for each of the reactions that I've written. So if I take 1299.5 and I subtract 2 times 393.5, and then I subtract 285.8, I will get 226.7. 226.7 kilojoules. And so this reaction, as I have it written, will use positive 226.7 kilojoules of energy in order to make this reaction happen.